Hello friends, this is Mr. Sarvesh Vazurkar. We are here for the session organized by Ballarpur Institute of Technology, Ballarpur, under AICT sponsored Prerna scheme for SC/ST students. Today's session is our session number 11, in which we'll see about the algorithms and mostly the design techniques of algorithms. This will be the content during today's session. We'll go to cover some of the important algorithm design techniques or algorithm paradigm. There are, as we know that there are various way of designing any algorithm, in which we'll cover every design technique we'll cover in brief, and at last we'll take one example related to one different technique, named it as the backtracking, in which we'll cover one Dijkstra's algorithm. This is the flow of our today's session. Firstly, we'll go with the various design technique, in which we'll cover divide and conquer, greedy algorithm, backtracking algorithms, and dynamic programming. Uh, yes. Firstly, we'll go with the divide and conquer. What is divide and conquer? As the name suggests, divide and conquer. We know that divide means to break the list and conquer means to merge. By breaking and merging the whole contents, I repeat, by breaking and merging the whole contents for a particular sorted order list or any different types of sorting, this divide and conquer strategy is used. Firstly, what we'll do in that divide and conquer, we are going to break the problem into smaller sub problem. We can solve each sub problem then, and after solving, we are again now combining the solutions to obtain the solution to the original problem. This is as simple as that in divide and conquer algorithm. What is the key details, or what are the various key details that we are going to keep in our mind while keep breaking the sub problems into smaller and smaller until the problem is completely get transformed into something entirely different. At that particular point, we conquered we conquered the original problem. What is that original problem and what is that conquering? See, as we know that in the problem is in hand, which is in our hand, is divided into smaller sub problems, and then each problem is solved independently. When we keep dividing the sub problems into even smaller sub problems, we may eventually reach at least at we may eventually reach a particular stage where where no more divisions are possible. With the help of an example, look like the example of merge sort. In the last video, we have again got the same point related to merge sort. Firstly, we are going to divide the whole list of elements. Assume that we are having the list of say 9 or 10 different elements, 10 different elements. We'll now divide that particular 10 different elements or 8 different elements into four parts, into two parts of 4 elements each. Let us assume we have eight different elements with us. We are break the whole list of elements into two parts of 4 each. Both the two parts are having 4 and 4 elements along with them, and that 4 and 4 elements are now again be divided into two different parts. That two different parts are further divided into two sub problems. That two sub problems are again further divided into one sub problem or one sub element. Then we have to divide the whole list of elements unless and until we'll get the where no further more divisions are possible. If not, if there are no further more divisions are possible, then we are going to arrange them in a particular sequence. It may be ascending, it may be descending, whatever. Accordingly, if we are assuming that whatever the small, we are assuming that we are going to arrange all the elements in ascending order, for example, and then we are now comparing the single element with each other and then conquer them. Conquer means to merge them. Conquer means to merge them. In this merge sort, we have the complicated task of sorting a bunch of values. However, sorting is a set of one value. However, it is a completely different problem as a trivial one in this case, where completely sorting a set of two values is not a travel, but it's still a completely different problem on one that can be desired as a conditional swap. Swapping is there unless and until we'll get the smallest element on the left hand side and the biggest and the larger element on the right hand side. Our list may not get sorted, isn't it? So these steps involve, say, firstly we are going to divide and break it into two parts. This step involves the breaking of the problem into smaller sub problems. That smaller sub problem should represent a part of the original problem. This step can generally take a recursive approach unless and until we have to do where no further problem or no further elements are divisible. At this stage, subproblems become atomic in nature, but still represent some part of the actual problem. Next, when the conquer parts comes into the play, that step receives a lot of smaller subproblems that to be solved. Generally, at this level, the problems are considered solved on their own. Secondly, after sorting, we are going to merge them together. When when the smaller subproblems are solved, at this stage recursively combines them until they formulate a solution to the original problem. This algorithmic approach works recursively, and conquer and merge steps work so close that they appear as they are. Originally proposed and efficient It can originally proposed an efficient technique to implement binary multiplication in hardware. It is very much useful for multiplying the polynomials and integer number, and we can also go with the help of that carrots bar multiplication algorithm. The key detail in this case beginning with is being with multiplying the two numbers of n bits is a complicated problem, but multiplying two single bit numbers is just a logical AND gate. The algorithm is nowadays used in cryptographic algorithm. There are various examples of that divide and conquer programming approach. We can solve the merge sort by using divide and conquer. We can able to solve the quick sort. We can able to solve the binary search, Strasson's matrix multiplications algorithm, or we can say we can also able to solve the closest pair problem as well. There are various different ways available to solve any computer problem, but the mention which we have just now mentioned, like merge, quick, binary, are some of the good examples of the divide and conquer algorithm. The key detail in this case is being multiplying two numbers of n bits that I have just now informed, which are related to your n bits as complicated problem, but multiplying two single bit numbers is just a logical AND gate. The algorithm is nowadays used in cryptographic applications where where the number arithmetic is very large in number, and in order of up to the thousands of bits it requires. In this context, the difference is being multiplied the numbers by n bits, where n is greater than the CPU register. N means any number of bits we can calculate, and then register size numbers can also be calculated over there. Runtime in which the runtime which is given by the following recurrence relation is equal to t of n is equal to 3t n by 2 plus theta of n, where the running time comes down to order of 3 log n is equal to order of n log to the power 3 is equal to order of n to the power 1.585. It is about by applying that subquadratic time as well. uh, Next is in terms of greedy algorithm. That is all about your uh, I can say that divide and conquer. Now we'll go with greedy approach. What is greedy? It is iterations. There are Iterations algorithm. Greedy algorithm is an algorithmic paradigm that can build that can definitely build up the solution piece by piece or iterations by iterations, always choosing the next piece or next iteration or next step that offers the most obvious and immediate that gives us very ultimate benefit to us in terms of time. As we know that we are studying the subject design analysis of algorithm, where we are always be using the optimal time. We have to always restrict with the optimal time and optimal space as well. So the problems we are choosing locally optimal that can also leads to global solution that are best fit for that greedy algorithm. That term greedy refers to the fact that the algorithm do this in a shorter sighted way. That algorithm do this in a shorter sighted way where they try to maximize the immediate gain, disregarding the big picture. It may be the whole picture is very, very big, but sorry, but they are dividing it into the parts and dividing into the parts, and then they can fail to determine a global maximum or minimum that may be any local or any some local maximum as well. This greedy algorithm is specifically designed, sorry, it is designed to achieve optimum solution for any given problem. In greedy algorithm, decisions are made in front from the given problem domain. As we are already aware, as being greedy, the closest solution or the minimum optimal solution that seems to be provide uh, whatever the optimum that we can going to choose it out. For example, if I have given you the task related to find the shortest path, you can choose from the choice, you can choose from the variety, and then you can able to find out the path wherever it can be or whichever it can be. Greedy algorithm are always try to find the localized optimum solution, which may eventually lead to the globalized optimum solution. However, generally greedy algorithms do not provide a globally optimized solution, so we'll not go into that matter. There are various different examples like activity selection problem, Dijestra's algorithm, Dijestra's shortest path find algorithm, Huffman code, optimal merge. Again, we'll see about the job sequencing problem, Kruskal's problem, uh, Kruskal's minimum. I mean, I can say like minimum spanning tree algorithm, Prim's minimum spanning algorithm, as well as fractional knapsack that can also be there in this uh, greedy algorithm. Next is when we are going to deal with any different algorithm design techniques, they don't necessarily fail. In fact, we can saw our fair share of greedy algorithms that are proven to obtain the correct output. We can saw all of these three very recently in the last videos like Disastras, Prims, and Kruskal's algorithm are all our greedy algorithm that I have just now mentioned. All are pathfinding algorithm where the shortest path where they have to choose which one is the shortest, they can able to select it from the list of given elements or given tracks, that which one is the minimum path and which one is the maximum. So we need to choose the minimum by applying this greedy algorithm. A classical example of this technique is the problem of producing the change, or in general, we can expressing a given amount of money in coins or minimizing the number of coins that are required. What's a greedy algorithm is there to compute this result? A classical example at simple way, I can again say at each iteration, put as many coins of highest denomination that fits. Highest denominations that fits, we are going to require as we are going to put as many coins as that can. The reasons that if you are choosing the coin of 1 from the coin of say 1, 5 and 2, if 3 different and 10, if 4 different coins are with you, you have to choose the highest denomination where and you have where you may get maximum amount of profit and maximum amount of rupees with you. In that case, I'm going to give that live example to you. If you assume that you have having the coin of 1, 2, 5 and 10 rupees, what happens? And you are able to choose only 5 different coins with you, or 5 coins with you. The limit is already been there. What matters? What matters? What matters? In that case, if you are going to choose that particular value, and you have to choose any 5 different coins from the given 4 denominations, in that case you need to choose the amount, or sorry, the value or the coin which gives you maximum amount of profit. What's a greedy algorithm? Which type of algorithm you are going to put it? You are going to put it at each iteration, put as many as coins at highest denomination, as I already said. But does it minimize the number of coins in the final outcome of the algorithm? Yes. You are I probably use that idea that can does, because with Canadian coins denomination it does works, but probably it does work, but it can be indeed fail. Any can anybody? No, it cannot be fail. But denominations are say 10, 8 and 1, and try to break it into 17. Those optimal is obviously 3 different coins of 2 8, 2 multiplied by 8 plus 1. But there are greedy algorithm that will tell us how do we require 8. We can simply go with 10 plus 7 multiplied by 1. That's it. In that case, this greedy algorithm can work depending upon the set of denominations. If every denomination is at least twice the next one is in decreasing order. Or you can simply choose any different value from that which gives you maximum amount of rupees with the desired denominations. Alternatively, if every denomination is greater than or equal to the sum of the smaller denomination, that Canadian coins meet these requirements. In cents, we can go with in cents, of course. The Canadian coins that are always be in cents. So 200, 5 and 5, 10 and 1. So if all this greedy short sight algorithm can fail, why do we bother? Why are they attractive? They are attractive just because they tend to be very efficient. To each iteration we look only at the immediate scenario. No need to look globally. We are always been selecting it from the given input. So always be optimistic. The number of coins are we should be minimum, but it gives you maximum amount of profit. Same thing is real with the job sequencing problem, where we have already given with the number of elements and number of jobs, and accordingly the profit of after executing that job. If you assume that if you have given say 6 different jobs, and the capacity to execute that 6 given jobs is like only 3 can be executed. What we can do, if we have given like job 1 is having the deadline 10, job 2 is having the deadline say 5, 3 is having 20, 4 is having 15, 6 is having 30, 7 is having 25 and so on. 6 is having like this, and the deadline along with the profit, the deadline is say only 3, 1, 2 and 3. In that case, you need to choose whichever will give you maximum amount of profit will be get executed first. Ultimately, Ultimately, the process is for that job sequencing problem is simply like you have to arrange all the different elements in the descending order or in the decreasing order of their profits, where the maximum amount of profit which is executed by applying or by executing one job which gives you maximum amount of profit will be get executed first, according to its deadline, of course. And then you need to pick up out only three different jobs, cause the capacity of that job execution algorithm or job sequencing problem is like only three in this particular case, in this particular example, I can say. It may be shifted, it may be changed accordingly, doesn't matter. But whatever the number of jobs that yeah, that you are going to execute it will be your will be your uh, maximum profit, or by executing all that particular jobs in a desired very desired time. On the other hand, it could not be yes, that non-deterministic polynomial is also be there. It could not be an example of a solution to a problem like non-polynomial complete problem, or a problem that can be believed in it. It may be interactable and a greedy algorithm that might be efficient alternative that can find a near optimal solution to you. This is all about your greedy algorithm. Now, the third part that we are going to see it right now is about the backtracking algorithm. What is that backtracking algorithm? How it works? We'll see just now. Yes, as the name suggests, backtracking. Backtracking algorithm can be seen as an optimized form of exhaustive search algorithm. Optimized, very smallest, properly analytical way. If you are able to solving that particular problem, is maybe a backtrack. We'll go with various examples. I am having lot of examples for this backtracking. Backtracking, we can try to possible try all possible combination of the things with early elimination of paths that lead to no solution. Backtracking is a technique that is based on the algorithm to solve the problems. It uses a recursive calling to find a solution by building a solution step by step, increasing values with time. Of course, time always plays a very vital role over here. It removes the solution that does not give rise to the solution to the problem of the problem that is based on the constraints which is given to solve the problem for you. Next is backtracking algorithm is applied to some specific types of the problem, where decision problems that are used to find a feasible solution of the problem. It is applicable on optimization problem that are used to find the best solution that can be applied. So that the best example of this backtracking I can give it to you, like Sudoku is the best example. Enumeration problem that is used to find all the feasible solution of the problem. In backtracking, we can see the algorithm that tries to find a sequence or a path, um, uh, or for any to the solution which has the small checkpoints from where the problem can backtrack if no feasible solution is found for the for particular problem. uh, Now there are only four or four different steps to solve the problem. If the current position is the goal state, then returns a success. If not, if the current position is at the end point, then we can return it failed. Else, if current position is not end point, explore and above the and repeat the above these two steps that I have mentioned. A good visual analogy is like think of the possibilities that represent by a tree, and we do a depth first traversal. This is the way of doing the searching or traversing. Like we know that there are two different ways basically which we are majorly used in terms of graph traversal, where the depth first search and breadth first search. But we have the advantage that in many cases before reaching the leaf node, we know that this particular path will lead us nowhere. So we just backtrack, and we are always going to try the next possibility at the previous level. What happens in that case? If we are not able to find a particular path, we can that will reach up to that will reach up to our goal, but at that particular moment we need to change the path. We need to keep backward, and then from that previous point we need to change the track because we are unable to get the answer. Classical example: eight queens chase puzzle. As we know that in the game of chess, queen really plays a vital role, where it can move forward, it can move horizontal, it can move vertical, it can move diagonal as well, at any number of places. But in that case, we need to find a placement for eight queens in a chess board, 8 by 8 chess board, such that neither one falls straight of capture, falls under threat of capture. It directly means that no two queens can crash each other. If it is in not in diagonal way to any other, if it is in not in vertical way to any other queen, and if it is not in the horizontal way of any other queen, we need to place that eight queens in such a way that no two can falls under threat of capture, like this. In the game of chess, we need to place this is the simple possible way where we can able to find out. But initially when we start it, we have to play, or we may start with the first one, where we can place the first queen in the very first block over here. But accordingly we are able to place all the different seven queens if we are placing like this. But it may not find the possible way to you. You need to backtrack yourself. There are many different possibilities to place all that eight queens in that 8 by 8 chessboard. While utilizing it or while going it, you need to change the position by applying the backtracking algorithm. You need to change the position of the previously placed queen so that no two queens can crash each other. At yes, look at this. At each column, each level of the search, we have eight possibilities. So we try, as we know that it is the box of chess is a game of 8 by 8 boxes. In that game of chessboard carries 8 by 8 boxes, and ultimately we have 64 back boxes with us. So we try each and every one move to the next level. If at some level we are unable to find at all the eight possibilities, they might be fail, then we backtrack. Then we backtrack. Go back to the previous level. If required, change the position of that previous level. Reportingly, that is that this one also failed at that previous level. We now move to the next possibility and keep trying unless and until you may get the final answer. When you get the final answer, that will be your final position. This is the key detail that most of the time we are going to discover early, that the current path does not work. For example, at the third and fourth column, we'll find that it won't work. Look at this: third and fourth column, it won't works. If in that case, we need to change the position of the firstly placed block, or of the firstly placed queen, which you have already placed in the first row or first column. Other classical example of this algorithm design technique, that is backtracking, is like turnpike reconstruction problem, in which we have n number of points are available in the line, wherein we have to give wherein we have to give given the distances that are saying in ascending order. Of course, ascending means to increasing order. Yes. In this problem we are able to find the Partial, we can also know that this particular problem is also called as, I can say that, partial digest problem, which is given a multiset of the positive numbers, all are in ascending order. Does there exist a set, and I can say like it is a multiset or a positive pairwise differences of elements which are already been there, and the complexity of this particular problem is uh, about to known, I can say. This is the example of that backtracking. Unless and until you are able to solve, unless and until you are able to place all the given elements and all the given values according to their distances, like this, x1 to x6, x6, and so on. And there are various key detail there are at each iteration. We have several possibilities, but some possibilities does not work because they lead to points with the distances that are not yet found in the set. So we need to backtrack and discard the current possibility that being considered at the previous levels to you. If possible, we can also go with that algorithm which is given to you. Next is in terms of that backtracking, I can summarize in again in a different manner. I can summarize in it in a different manner where uh, where uh, n queens problem, or I can, yes, it is again possible. We can able to we can able to place for the four queens in 4 by 4 chess box. We can able to place eight queens in 8 by 8 chess box. We can able to place n queens in n by n chess board, and we have to place all that n queens on the board in such a way that no two queens can attack each other. A queen will attack another queen if it is placed in horizontal, vertical, or diagonal points, as I already mentioned. So the binary output is again being possible, like wherever there is a wherever there is a queen that we are going to place in each row or in each column, we need to put one, and rest all the elements are zero. For solving n queens problem, we try to place all the queens into different position of one row, and checks if it clashes, or oh yes, if it clashes with other queens or not. If current positioning of queens, if there are any two queens attacking each other, if they are attacking, we will backtrack to the previous location, and then queen can change its, and then the previously located queens can change their position, or they can swap their positions accordingly. Yes, that rat maze problem is also been there, that can be able to solve by using this backtracking. We are having n by n maze, and then first position is like, with the help of that matrix we can again able to solve. Using backtracking, we can this problem will go step by step to reach the final goal, and then that 2D array, or I can say like matrix multiplication, can also be able to solve by using this particular problem for that backtracking algorithm. Last and next is dynamic programming. What is that dynamic programming? Yes, the basic idea with the dynamic programming is to work with the problem that is broken into slightly smaller sub-problem. What is dynamic? As the name is suggested, it is dynamic. There are various variations to solve a particular problem with various solutions. Where some of these sub problems can overlap, whereas in terms of it is having the approach which is very similar to divide and conquer, in breaking down the problem into smaller and yet smaller possible sub problems. But unlike divide and conquer, I can say like, unlike divide and conquer, these sub problems are not solved independently. We need to solve them unanimously, rather than the result of these smaller sub problems are remembered and is used for similar or overlapping sub problems. Next is dynamic programming, is we can use where we have where we have the problems which can be divided into similar sub problems, so that the results can be reused. Mostly these algorithms are used for the optimization. These dynamic programming algorithms are used for optimization. I can also say like a straightforward recursive solution is inefficient, since we can solve the same sub problems over and over again. The main detail with a dynamic programming solution is that we can store the solution for the various sub problems that we have already solved. Yes, best classical example is that of recursive implementation of a function that can determine a Fibonacci number. Yes, Fibonacci number we can repeatedly calling itself again and again, which can be neatly implemented as like this: integer Fibonacci, integer n, where if n is less than or equal to 2, return 1, else it is n minus 1 plus n Fibonacci n minus 1 plus Fibonacci n minus 2. That's it. It is normal simple example as that as can. This is the way of applying the dynamic programming. Way of applying or using the dynamic programming. In simple words, the problem should be able to divide it into smaller overlapping subproblems, and the optimum solution can be achieved by using an optimum solution of the smaller subproblems. Dynamic algorithms are memorization algorithms as well. In terms of comparison, in contrast to greedy algorithm, where local optimization is addressed, here the dynamic algorithms are motivated for the overall optimization. We are not going to see for this particular step optimized way. No, it is for the complete problem which is in optimizing mode can be there. In contrast to the a complete way for an overall optimization of the problem. Uh, in contrast to divide and conquer algorithm, we can say that we are combined to achieve any overall solution. Dynamic algorithm use the output of the smaller subproblems and then try to optimize the bigger subproblem. Where dynamic algorithm use memorization to remember the output which are already solved subproblems, and then Fibonacci number series, knapsack problems, towers of Hanoi, are the best examples that can be able to solve by using this dynamic programming. Yes, one more important algorithm I can able to highlight over here is like the Floyd Warshall algorithm, a Dijestra's algorithm, project scheduling, optimization scheduling can also be able to solve by using this dynamic programming, where we can use the both top down as well as the bottom up manner, and of course most of the time referring to the previous solution, output is cheaper than than recomputing it in terms of that CPU cycles. Yes, computing f6 that can involves computing f5 and f4, but then computing f5 requires the computing f4 and f3. It is like the previous mode, like previous, unless and until you are able to solve the previous one, you are unable to solve the next one. That's it. Hopefully, you can see the exponential nature of that redundancy. 6, 5 and 4, 5, 4 and 3, and so on. In the above example, it might seem like we are doing no more than twice as much work. But F3, for example, it needed indirectly by F6, both through the path F5 and F4, F5 and F4, in which it is completely been redundant. Each extra level multiplies times something, and the number of times it can lower that are f of k that are computed over there. This is the normal, I can say the concurrence relation for that recursive function, which is t of n is equal to t of n minus 1 plus t of n minus 2 plus order of plus theta of 1 or big O of 1, but that the same recurrence relation as for the Fibonacci number themselves, where the additional term added is order of 1. Thus, T of n is less than or equal to f of n, which is already been given, and the T of n, which is grows at least as fast as sequence of Fibonacci number, where which is completely known as a part of exponential. The approach for the dynamic programming is then storing the computed value so that we don't we there is no any need to redundantly compute them over and over. We can also able to notice that we do not need any exponential amount of storage, and the amount of storage which is required is completely in linear format. The amount of redundancy was exponential, and so no computation of smaller number of values may repeatedly for a total exponential number of computations. As I have just now mentioned, there are two different approaches of solving the problem. It is like a top-down approach, I mean top to bottom approach, and second one is bottom to up approach, I can say. But what is that top to bottom and how it works? That top to bottom, it can sets up an associated array which where each time that the function is requested to compute that the function is requested to compute any single value, where it can firstly check if the value is in the corresponding location in the array or not. And if it is in if it is use the value or uses the value, if it not, it can compute the value and store obtain the result in the particular array which is given to you. This is step by step execution of each and every problem of each and every step is called as a top down approach or top to bottom approach. And second one is bottom to up or down to up, I can say bottom to top, where we can say start at the base case and explicitly we are going to grow up. We can able to calculate the upper values in terms of which are already calculated the bottom values. In other words, I can say like bottom up approach can also be able to solve the reverse engineering problems over there, which are completely the part of dynamic programming, which are completely the part of that dynamic programming. Again, I can say like uh, uh, a matrix multiplication or associative abcd can also be done. It is in terms of a in the whole bracket bcd, or I can again distribute it in terms of a which is there in which is there in bracket, and rest is not in bracket. When considering all the possible arrangement, we are somehow able to find the arrangement for the smaller sequence that can be repeat. So we would end up redundantly by doing these computations. We can able to solve any different problem in that dynamic programming approach. There might be uh, there might be any different algorithm that can able to solve, which is aligning by alignment by stretching the subsequence. Whenever we can see any recursive solution, we are repeatedly calls for the same input, and that's why we are going to optimize it by using the dynamic programming. This idea is very simple to store the result of the sub problems, and this is very interesting application in there are very interesting applications in speech recognition as well as in rhythm recognition. We can find it out in the live applications like music, that dubbing, and that matching of the music search applications as well. This simple optimization technique reduces the time complexity from exponential to polynomial. And for example, if we are able to write the recursive solution for Fibonacci numbers, as we have just now discussed, previously discussed, we can get exponential time complexity. And if we are optimizing it by storing the solution of the sum problem, the time complexity reduces it to be the I can say like linear one. There are various sub or advanced concept like this bit masking. We can use that dynamic programming also. uh, Digital dynamic programming can also be the part of that elements. Next is single source shortest path. What is that single source shortest path? We know that we are able to solve any different problem by using this single source shortest path, where the path is given to you along with the weights, along with the way at means the direction. Since it is having the directed graph, where s, there are four different nodes from s to say x, in which in which we are able to find it out the shortest path to reach from the source to the destination, say x. We can able to determine the distance from vertex x. We can able to identify the path of the each vertex expressed concisely as a shortest path tree, and then we'll move forward like each vertex has a pointer that to the predecessor on the shortest path. We can also able to construct a tree from the from that given path, where all the nodes are to be same, but from the given graph we can able to draw the tree as well by applying or by using all the shortest path like this. If there are from s, there are two different paths that can be move accordingly. in which one is having the weight 4 and another path is having the weight 2. Why we are going to choose 2? Of course we are going to choose 2, but obvious why. The reason is it is having the smallest value. So we'll choose that particular path like S to B, and from B there are again two different paths. One is going to F, which is having the value 7, and another is going to C, which is having the value say 3, or which is having the weight say 3. We'll choose that particular path, and completely by covering all the elements in the given graph, we can able to find the shortest path to visit all the nodes in the given tree or in the given graph. Can say this particular problem is called as single source shortest path. Yes, if P is the shortest path from S to V, and if T is the one of the path P, and then the segment from S to T is the shortest path between S and T, we can use that particular way. The reason it gives me the smallest weight to reach from the source, from the source say S to the destination say V. Why? Assume all edges have non-negative cost. Non-negative, it means it may be zero or it may be more than zero. That's it. Any positive value will be the weight for that Dijkstra's algorithm. Initially, we can start it with S, and ds is equal to 0, where infinity it may be not equal to S. Uh, while S is not equal to V, I can say that means source is not equal to the destination. We'll choose V in V to S with minimum d of V, and add V to S consequently. We'll go that single source, of course the source is only one, but to reach to the destination, that X is the destination, or sorry, that V is the destination. V is the destination. We need to find the path from S to V, which will give you minimum weight. Look, if we go with S to U, it gives you the weight. It requires one weight, S to U. From U to V, there is a weight 3. So the total weight by using the first track, it requires 0 S to 1, sorry, S to U and U to V, that is 4. By going with the different track, S to X and X to S to X and X to V, it gives you 4 plus 1, that is 5. And if we are going to use the third different path, S to V, V to X, S to V, V to X, and uh, S to V, V to X, and X to V again. In that case, it may be 2 plus 2 plus 1, again it will be 5. And there may not be any different path than this to reach from the source to any destination. So accordingly, we need to choose whichever is the shortest path, that we need to choose it out like this. That we can able to solve this particular problem by using that Dijkstra's algorithm, as I already mentioned. With the help of this given algorithm, see in the given graph, I have mentioned that 5 nodes problem, where I can able to solve it with the help of that matrix, the Dijkstra's algorithm. In round 1, I have mentioned the rounds and the first column is having the vertex which we are going to add, and all the columns are nothing but the nodes of the given graph. Definitely, if we are using S to A, it is 1, A to C it is again 1, and so on. We are sequentially adding one by one elements accordingly. Dijkstra algorithm is a part of greedy algorithm where elements can be committed to the solution by order of minimum distance. Whatever the minimum distance is there, we can we can only use that itself. We can only use that itself. Rest of the thing we are not at all going to use. The reason we are always finding there for the minimum path. There is one correctness proof, which is where elements in S they are having the correct label, and that is the key. They are having that proof of when V is added to S, it has the correct distance label. The Dijkstra algorithm is simply there for finding the shortest path from a particular node, where it can able to call the source node to every other node in a connected graph. It produces a shortest path tree with the source node as a root. If it is profoundly used in the computer networks, it can able to generate the optimal routes with the it can able to generate the optimal routes, of course, with the aim of minimizing the root cost. These are the best applications of this, where we are able pathfinding algorithms where we can able to solve it, and we can apply. It is applicable in the at high level. It is applicable it in the to find the train routes, to find or to create the road maps as well. Where the input in Dijkstra algorithm is like a graph that is representing a network and a source node, of course, and the output is nothing but the shortest path tree. That's it. Which with S as a root node, or I can say like a source node as well. Nextly, we can also able to solve it by using the proof, like let V be the vertex in V2S with minimum dv, and with the age that is u and v, where you will let p be the sum of the path to v, where suppose p first leaves s on the age x comma y, like which is already given over there. Then p s of x is plus cxy plus p vy can also be the part of that. And if you are using that length or weight, that len stands for length, and or you can able to use that, replace that len by weight, that is wt or w. You may definitely get the perfect answer of this Dijkstra's. Draw a small example of negative cost tree, where yes, negative cost tree is also matters like this. uh, Bottleneck problem. Yes, you can able to solve this particular problem as a part of classwork. This is an algorithm that can fails on this example. But define the bottleneck distance for a path that need to be find the maximum cost age along with the path. That can also be possible. You can again able to find out the maximum path for the same. Simply you have to mention all it you have to mention all these things with the help of various iterations, and in each iterations the values that you are going to choose it, that should be maximum. I mean that maximum path finding problem or bottleneck distance can also be able to solve by using this Dijkstra's algorithm. Initially an array of distances, where the size v is there, along with the distances 0 to infinity. It may be 0, it may be infinity of at it may be any different cost here. It is 5, 6, 2, 5, 3, and 4 accordingly. An array which is containing all the nodes in the graph, and when the algorithm runs into the completion, that complete queue or that complete list will be get empty, which is further divided into various nodes that can be added. When the algorithm that runs into completion as will contain the nodes in the graph, we can repeat the same different steps again and again, unless and until we'll get the final answer. This bottleneck shortest path can also be possible by applying this negative weights as well. So you can able to find it out by simply following all these rules of Dijkstra's algorithm. The question arises how to handle the bottleneck distances. How to adopt the Dijkstra algorithm to handle the bottleneck distances. Does the correctness proof still apply? Yes, the correctness proof can be still apply. Which are the major contributors? The major contributors are like this. Mr. Eitzer Dijkstra's was the most influential member of the computing science fundamental generation, and among the domains in which the scientific contributions they are fundamental, they have designed various algorithms, they have designed various programming languages, program design, operating system, distributed processing, and so on. Negative cost edge can also be there in terms of disasters. We can assume the positive cost edge itself, but for some application, negative cost edge makes sense. Various of some of the applications it can be applicable, and the shortest path will not define in if the graph has a negative cost cycle. Negative cost cycle is not applicable over there, and the topological sort can be used for solving the shortest path problem in a directed cyclic graph. Yes, that Bellman-Ford algorithm finds the shortest path in a graph with negative cost edges, or it can reports to the existence of a negative cost cycle as well. With the help of this normal example, I can able to solve any algorithm that can assume, of course, the weights are of non-negative. Non-negative means I have already mentioned it is from z it is 0 to say infinity positive. Yes, that minimum cost spanning tree problem can also be able to solve by using this Dijkstra's, where we can demonstrate it by different greedy algorithms that it can provide the proofs that the algorithm works. And what is that MST? MST, that minimum cost spanning tree. Hold on. Yes. Uh, it can be demonstrated by using three different greedy algorithms, where we can provide the proofs of the algorithms, and that minimum cost spanning tree is nothing but a graph where it is connected and there is no acyclic. As we know that the definition of a spanning tree is simply like it is an undirected graph. A spanning tree, that the graph is a subgraph which where that is a tree and that can join all the vertices. A single graph can have many spanning trees, of course we know that, and there are various several minimum spanning trees that are of same weight, having the minimum number of edges or minimum number of weights. If the age uh, and if the age weight of the given graph are same, then the every spanning tree of that graph is definitely been minimum. This is a complete minimum spanning tree graph where from the given set of given graph I have highlighted the path. I have highlighted the path from a particular source to the destination, or when it can able to visit all the vertices of the graph by having the minimum values, by having the minimum weights, not values. Of course, if you are choosing the values, ultimately your weight will be definitely minimum. As we know that it is not looking at the local level optimization, it is looking at the global level optimization in this approach that these extras. So that's why I have chosen A to E, which is having 6. From E there are three different paths, E to A, E to C, and E to G. We have chosen E to C because it is minimum. Rest to reach up to the node G, F, we are choosing the minimum one, and at last F to B 8. Uh, B to B is adjacent of 1 2 3 4 5 different nodes, but we have chosen the remaining node S, which is there, which is about to left by which is about to visit it from B. So that's why we have chosen B to S, which is having the weight 2. S to T, it is having the weight 3. T to U, it is having the weight 10 itself, and U to V, it is having the weight 1. The overall total of the whole weight should be minimum by applying by as compared to other different tracks or as compared to other different paths. So greedy algorithm for minimum spanning tree, it can be extended by the tree which is including the cheapest ongoing edges, and add the cheapest edge that joins the disjoint components, and delete the most expensive edge that does not disconnect the graph. That graph disconnection is also matters. And if the graph is completely get disconnected, there is no any use of that digextras or prims or cruscals, any different type of algorithm. uh, in Prims, we can also construct the MST by using Prims algorithm. It can be starting from vertex A and label the edges in order to of insertion, of course, and it can construct it the yes, in Prims it can find the cheapest outgoing edge, and in Cruscals add the cheapest edges that joins the disjoint components. It means the link way is there in Cruscals, and simply we are able to finding out the normal smallest edges, smallest value edges can be there in Prims. That is the only difference in that Prims and Cruscals. So ultimately, this is the proofs for optimality, where we are able to find out the minimum cost spanning tree for the Prims as well as for the Cruscals algorithm as well. This is the normal proof, optimality proof by that can be able by computing the MST, that is minimum spanning tree, and Kruskal's algorithm can also be able to find out by computing the MST, that is minimum spanning tree itself. So this is all about we can able to define the clusters as well, and this is complete way for finding the path is called as the K clustering algorithm. This is all for today's session. Over to you, Neeraj sir. Neeraj sir, my voice is clear to you?
Yes, sir. Sir, am I audible to you? Hello.
Yes, sir. Yes, sir. Yes, sir.
Okay, sir. I'm ending the session. Thank you so much.
Thank you, sir.